is a quick update on graphs, metric spaces, and groups. So I want to finish up this natural spaces story and get it somewhere posted. And here's a little bit of organization, what I know. I don't know much yet, but first of all, the definitions. We have graphs, which are natural if they define a natural metric space, and a metric space is natural if it can be upgraded uniquely up to isomorphism to a metric group where the translations, left translation, right translation, or inversions are isometries. So it's quite an interesting theme where different structures come together, and once we have this group, we have a dynamical system also. We have a time, G, acting on itself. And so it's kind of interesting to see what is natural. And last week, half of the week I was spending on a fool's errand with finding this ultra-finite algebra, where Taylor works also with a symmetric derivative. I'm now almost sure that it doesn't exist. It's kind of funny. And that we have to kind of get to this dihedral structure where you have to kind of double up things, and you have to have two Taylor expansion on kind of two worlds. And this duality of kind of this dihedral structure also appeared in graph theory. Naturally, this is the connection graph. If I look at the connection graph of either Z or the cyclic graph, then what happens is this is a natural graph. So there's a unique group structure on this graph, and I put it here. So it's a non-abelian group, the non-abelian group Dn. If you start with Cn, you take the connection graphs. These are the edges here, and these are the vertices. So what happens is that there's a unique group structure such that all translations are isometries. So that's very interesting. And also here we have seen that the real numbers, they are natural. There's only one group structure here. So there are other spaces. I know, for example, this dihedral version of the circle, which is the orthogonal group of 2 times 2 matrices. Orthogonal 2 times 2 matrices. It's a disconnected Lie group, so it's a semi-direct product, and that's also natural. This metric space defines the group structure. And most spaces, of course, are not natural. We need kind of some large symmetry. We need the symmetry group. That's what I wrote down here. So the isometry group has to have at least the cardinality of the space itself, so that the space itself can be this, because the space itself will be then part of this isometry group. And also here, that's kind of a simple observation, is that the number of vertices which you have in a graph has to divide the automorphism group. So the automorphism group has to be already quite big. So that's quite an interesting thing when we look at the automorphism group of a graph. You have a lot of things. You have the Lefschetz. You have Lefschetz numbers for every point, for example, and have this Lefschetz fixed point theorem, which tells you. So in this case, the Lefschetz for every reflection, the Lefschetz number is 2, and for every translation, rotation, the Lefschetz number is 0. There are no fixed points, but for reflections there are 2 fixed points. And so each of them has index 1. And so what we have is then we can look at the average Lefschetz number for such a natural graph, and that's always 1, which is kind of so this is a fixed point theorem here, which can be used. Lefschetz fixed point theorem, which generalizes the Brouwer fixed point theorem. So in the case of metric spaces also we need a relatively large symmetry. If you look, for example, at this space here, so this space is a disk, and so the symmetry group is again, it's just the rotation group, and O2R, and that's not big enough here to cover that whole thing. So that's not natural. While here, this is natural. It's also natural if you take 2 copies. If you take 2 copies of this is O2, and so then we have kind of on one copy we have rotations, on the other we have reflections. So this is quite an interesting thing. It's also interesting that if you take the Cartesian product of manifolds, this you can put a metric on it so that it's natural. You have just to break the symmetry. So in this case, for example, to see that R2 is natural, you just take a metric which is you don't have additional rotational symmetry, and then this is a natural group. There's only translations which then work. The reflections also work, but the reflections put you onto a disconnected part, but that's a connected space here. So this is so R2 and Rn in general is natural. As for groups, we have seen that every group of prime order is post-natural because there is only one. There's only one group up to isomorphy which has such an order. The diagonal group, that's kind of a very important case. It comes from this space here, and so if you look at the structure of the abelian group, there's a fundamental theorem of abelian groups. So most of the abelian groups are natural. Not all. For example, you can take powers of a prime, z of a power of a prime, for example. And so here's an example which I also understand a little bit better for small groups, like groups of order 8. There are 5 groups of order 8. So there's the quaternion group, there's the cyclic group. So they are not natural. I'm now sure about this because there are only 4 possible parameters you can tune for a metric here, just in order to that it's invariant. And that's not enough. So with all this freedom, you still have also this group here. You have also this group here as a D2 cross Z2. You still have also this group structure available. So these are not natural. These are natural. These are all natural groups. And so you have to break a little bit more symmetry here so that it excludes the Q8. And so for symmetric groups, I don't know yet. So this is kind of funny. For example, the symmetric group is 4-element, 24 element group. I don't know whether it's natural, but S3, that's just because it's a dihedral group. That's natural. And actually, I talked about this last year. Kind of that's the Rubik cube for the 2 times 2 times 1 Rubik. So what happens? A B A B A B, right? So there is kind of exactly this dihedral. So this is actually a dihedral group, and it's one of these natural groups. So I don't know. We need more theory to kind of, for example, see whether the Rubik cube, which is a finite group, is natural or not. So so that's natural. This I don't know whether it's natural. This is the symmetric group with 8 elements. That's just the permutation group of the corners, and then we have these are the parities of the edges, and this is the permutation group of all the edges, and that's a subdirect product. So it would be nice, for example, to know if the subdirect product of groups which are natural, and then it would also be good to know whether S8 or S12, just in general, Sn is natural or not. Didn't make progress, but I decided to move on. I have to get that out and just write down what I have. So it's an interesting theme where lots of things come together. Also a little bit of topology comes together. Some dynamical system theory. This is time, a theory of time comes in, and naturalness is kind of, I think, a nice name, because nature wants to tell us something when we look at, for example, why do we have to double things up? And this is not the first, I mentioned this last time, it's not the first case where such things appear. There is, for example, in non-commutative geometry, there is the Conlott model, where kind of you look at the Kaluza-Klein system, where you have just a discrete space. Additionally, you add another dimension, and so you take a space and you double it up, for example. So that's becomes non-commutative in general. And here also, I mean, this is kind of a baby version, where you go from Cn, you go to Dn, where you double things up and you get to a non-commutative group, but it's now suddenly a natural group. So from this kind of a simple observation here, because the number of elements of the group has to this is actually, it has to be a subgroup of this has to become a subgroup of the automorphism group of the graph. And so what we can say, for example, if the number of vertices is equal to the cardinality of the automorphism group, then we have a natural graph. And this Dn is an example, right? The Dn has 2n elements, and the automorphism group is that. Okay, that's it for today.